Good afternoon, everybody. Welcome to another exciting afternoon, cloudy and maybe rainy afternoon of organic chemistry, Chem 170, with your host, me, Dr. White. Now, a couple of things. First of all, if you missed it yesterday, I went through the answers for test number one. I cut it out of the video as I promised. But if you need to see any, always feel free to see me after class or come to my office hours. Now, this week, yesterday, and also tomorrow, because the Stanley Cup playoffs, uh, I moved my office hour to 5 to 6, which I'm going to send out an email sometime today or tomorrow, and or maybe even Thursday, because I've been real busy, uh, asking or giving you a choice what office hours, because my 6 to 7 roughly hasn't been convenient for many of you, like almost all of you, and I'm trying to get a better time. But tomorrow will be 5 to 6. Now, yesterday I forgot something. What did I forget? Show and tell. Yesterday we were talking about distillation and how to do a distillation lab, and I forgot this. This is a micro distillation column. You put a round bottom, which I happen to have. I got these on eBay. This you grease. This goes in here. You heat it up. Have a thermometer right here. Vapor goes up here, and you got this really cute, tiny little condenser. Remember, water goes into the bottom, out the top. Now, this is for vacuum distillation, which I didn't talk about. When you lower the vapor, the pressure of a system, the boiling point decreases because the boiling point is when the vapor pressure equals atmospheric pressure. So if you have very sensitive, temperature sensitive materials, you do what's called a vacuum distillation, which I didn't talk about yesterday. But this is identical distillation head, it's called micro distillation, or Contes makes it. I don't know if they're still in business or not. And in grad school, this was my best friend. No, I didn't steal this from Michigan State. A number of years ago, I got one on eBay. Usually, these are very expensive. Back when I was a student in the mid 70s, these were about $150 a piece. I got a good buy on this. And same thing with the, aren't they cute? Round bottom flask. Let me put this somewhere safe. I thought I'd mention that. All right, a couple important things. Uh, if you look at the schedule, we're ramping up things. We're moving at a faster pace now. And that happens in the spring and also fall semesters. What that means is tomorrow, I will go through the alcohols problem set. Thursday, I will go through the ethers and epoxides problem set. This week, I'll finish. What am I doing for test number two? That's why I will finish probably today, if not tomorrow, for sure Thursday, ketones and aldehydes. On next Tuesday, I'll go through the ketones and aldehydes problem set, and I'll do the review for test number two, which is coming up a week from this Thursday. Remember, this Monday is the 5th of July, and because the 4th falls on a Sunday, it's a holiday, and ECC will be closed, which means no uh, lecture. But I will do, if you don't tell anybody, I'll show up for my office hour in case you need some help. But that's the 5th. Don't tell anybody I'm doing that, but I'll do that. All right. I think I covered everything. To start off on a good note, a couple of things. First of all, have any of you happened to think about when you go into a gas station and you look at a gas pump and it says this gasoline contains up to 10% ethanol, that's an alcohol? Did you happen to, and you don't have to buy this, but if you happen to be in a liquor store, or I guess Jewel sells it, and you look at a bottle of hard spirits, like the good stuff, vodka, Grey Goose or Absolute. Oh, by the way, Costco's French, not they're American, they're French vodkas are a real good deal. It's about this close to Grey Goose. And I'm an expert in vodka. But anyways, do you think about that contains ethanol, which is an alcohol? Or did you happen to look at a bottle of rubbing alcohol and that contains 2-propanol, also known as isopropyl alcohol, in water, and that's an alcohol? It's all around us. Or finally, do you happen to look at a bottle of nail polish remover and look and say, oh, that has acetone in it. It's a ketone. Remember, organic chemistry is all around you. I wish I had a wider screen webcam, but I stole that from SpongeBob. It's all around you, and it won't hurt you to think about it when you're not in my lecture. All right. The other thing I thought we'd do right now is do something fun. And it's time to play a fun game with Dr. White. What's that fun game? Well, let's find out. Everybody see my whiteboard? Thumbs up, people. Thank you. And that fun game is circle and name the, I'll print it. And the fun game is circle and name the functional groups in the following molecules, 2 points each. And let's do some. Oops, wrong chapter. Right chapter. Let me clean this up. And the question is A, B, C, D, and E. Don't name them. Just circle and name the functional group in each one or groups, 2 points each. Have fun, because this is a fun game. I'm going to go take a walk around the block and come back when you're done. No, I'm just kidding. It's Terrible Humor Tuesday. And again, I don't want the IUPAC name. All you have to do is circle and name the functional group, 2 points each. When you're done, give me a thumbs up. or any other emoji that Zoom has. I see one person done. And I see two. Oh, someone used the party horn or whatever that is from New Year's Eve. All right, I think everybody's done. Is everybody done? All right, let's do this. Circle and name the functional group, 2 points each. We look at the first one, look for what's different. What's not carbon, what's not hydrogen, what's not a carbon-carbon single bond should get your attention like that. And if we look at the first one, let me go to a different color, hydrogen and oxygen on a carbon. What is this? It's an alcohol. Now, I didn't ask you to do this, I will, but it's an alcohol. Oh, look, second one, B, oxygen, carbons here, carbons here, ether. Oh, let's see, carbon double bond to oxygen with a hydrogen and carbons. And what do we call that? An aldehyde. And let's look at D, another oxygen. And it's double bond to carbon right here. But it's got carbons here and carbons here. So carbonyl with two different R groups, or they could be the same. That's a ketone. And remember, ketone is not spelled with a Y, but I'd never take that off on a test. Now we go to E. And I threw everything in there but the kitchen sink. And ooh, hydroxy group on a carbon, alcohol. Oxygen with carbons here and here, ether. Ooh, more. Oxygen to carbon. This is a hydrogen. And carbons here. What do we have? Aldehyde. We're not done. There's one more oxygen. Notice this double bond to carbon here with carbons here and here. And what is this? It's a ketone. And that's how you play that fun game. Circle and name the functional groups, 2 points each. I hope you all enjoyed it and had a good time. Now, time for a, excuse me, important public service announcement from me, Dr. White. I hope you all enjoyed the good scores you got in test one. Test one, historically in this class, is always this, not always, but most of the time, the test that students earn the highest average. Test two, coming up a week from this Thursday, is the test historically that students learn the lowest average, but not always. Last semester, they did quite well. In other semesters, but routinely it's not. Why? Because there's a lot more reactions and there are harder ones. Do the practice problems, do repetition. That way you'll do good on test two, because it's a lot harder than test one. But if you do the practice problems, it won't be harder. You'll do well. And that's my public service announcement. Any questions? Any questions on that? Fun game. Circle and name the functional groups, 2 points each. Well, in that case, let's move back to ketones and aldehydes. And was it yesterday or Yesterday I got into a little of this. I had some time. We're talking about the formation of acetal and ketals, which I'll never ask you what an acetal or ketal is. And here's one way of writing this general reaction. Well, let's go to my whiteboard. Better ask. Thumbs up, people. You see my whiteboard with a reaction on it? Thank you. All right. You take an aldehyde or ketone. If R prime is carbon, it's a ketone. If it's hydrogen, it's an aldehyde. React with not one, but two molecules or moles of an alcohol, acid catalyst. Keep your eye on the carbonyl carbon. That's where the fun is. And what's attached to it, R prime or hydrogen, and R double prime stays there. And then there'll be two oxygens, and on each oxygen is the R group from the alcohol. And we went through some of these, and I thought I'd give you one more to try on your own. And here it is. What would be the organic product or products for the following? Remember, these are building blocks or tools that we make molecules with. And this one, I'll show you this general reaction later on. Mother Nature uses this to make starches. So if you like all those good things that Dr. White really shouldn't have, like potato chips, french fries, and pizza crust, they have starches in them, which Mother Nature uses this reaction, but not with these two materials, with other stuff. I hope you all did enjoy that fun game, circle and name the functional groups, 2 points each. And I should mention, let me do this. It's a fun game, but think about it. If you can't identify a functional group in a molecule, how are you going to name it? You can't. If you can't identify a functional group in a molecule, how are you going to know how to react it? You can't. So even though it's a fun game, it's a very important skill. Plus, it's 2 points each. All right, I think everybody's done. So I better get to work. And the question is, give the organic products or products are the following, and look for what's different, what functional group. And here we have a carbon, double bond, oxygen, carbons here and here. That's a ketone. Now, it could have been an aldehyde if R prime or H. It's not, and it's in a ring, which means our double prime and our prime are connected together. Ooh, two of something. That's unusual. Carbon, 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 hydroxy group on a carbon, alcohol, and H plus acid catalyst. And what do you get? Keep your eye on the carbonyl carbon. What's attached to it? R prime or H, and our double prime are still attached. Oxygen, oxygen, and then my two R groups on those oxygens from the alcohol. Well, this whole thing here is my R prime and R double prime, which I can just redo the ring. Don't forget the methyl group that comes along for the ride. Here's this carbon, which is this carbon. It will have 2 oxygens. And then my R group comes from the alcohol, which is this. And notice the N carbon has the hydroxyl group, and that's the carbon bonded to my oxygen. And over here, and that's the molecule you get. And that would be a ketal, which I'll never ask on a test. Let me not run away and let's take a look at it. So you can see if you did it right. I hope you did. All right. Now the question is, well, you know how to make hemiacetal, hemiketals, and you know how to make acetals and ketals. What good are they? Well, it turns out Mother Nature found out what good they are. Now, I should remind you, the reaction I just did in the previous one and the next two, I will never put a synthesis problem on a test with that, because at least as of today, the Supreme Court has still outlawed cruel and unusual punishment to students. So I won't, and I wouldn't anyways, you know, Dr. White by now. But what do you do with those? Well, you break them down. And how do you do that? You react them with acid and water. Let's assume you were all in our classroom together. We were face to face. And we're in a classroom, not a lab. And I'd ask you all, hey, where can I find, I wouldn't say, hey, I'd say, everybody, where can I find acid and water real quick in our classroom? And a lot of students would be going, I don't know if they do this or that, but they do. I wonder. And I'd say, you know where you find it? In your stomach. Your stomach has water. I've been drinking water today. And one of the miracles of life to me is in your stomach. And I think I'm not, and here I'm a chemist, not a physician. I never took anatomy and physiology, but I think it's your larger small intestine too. But in your stomach, you have cells in your stomach wall that synthesize hydrochloric acid, SH plus. That's always amazes me. See, I'm amazed right now. And Mother Nature uses that to do some reactions. Let's talk about two. First one I have labeled reversing hemiacetal or hemiketal reaction. I could have also called acid hydrolysis of hemiacetals and hemiketals. And if we look here, what do we have? This is when R prime is hydrogen, it's a hemiacetal. When R prime is alkyl, it's a hemiketal. And the key is there's only 2 places in all of organic chemistry where you have 2 oxygens single bonded to the same carbon. I'll say that again. There are only 2 places in all of organic chemistry where you have 2 oxygens bonded to the same carbon. And this is one, the next one I'll show you too. And they both give the same product. And here we're reacting this with water and acid. And what you do is you get back the ketone or aldehyde plus the alcohol you would have used to make that compound. It breaks apart. And this happens in your stomach. Oh, I better scare you. If you haven't figured it out, you're a walking organic chemical plant. There's a lot of things going on in your stomach and all over your body. That's organic chemistry. And it uses a lot of the same general reactions I'm teaching you. Scary, isn't it? You're a walking chemical plant. You are. So let's take a look at this reaction. Now notice I drew above the arrow water plus H plus acid catalyst. I could have switched to, I could have put H plus slash water. Now, oops, I'm a step ahead of myself. Eh. And now, what's different in this molecule? Oh, oxygens, two of them, one with a hydrogen, one with an alkyl group to the same carbon. I've got a hydrogen and carbons here. So if I have a hydroxyl group, oxygen, R, then I have R prime, but in this case it's hydrogen, and R double prime. This is a hemiacetal or hemiketal. When you hit it with acid, react it with acid and water, you get back the aldehyde or ketone you would have used to make that compound, plus the alcohol you would have used to make that compound. Whatever carbon this oxygen is on is the carbon the hydroxyl group is on your alcohol. Whatever carbon this oxygen is on here, the hydroxyl group will be on that carbon. So here's my R prime, here's my R double prime, here's my R group, and therefore I keep my eye on this carbon, which is this carbon, which becomes that one. What's directly bonded to it, R prime is H, R double prime is two carbons, will be bonded to it. Then it's double bond to carbonyl, and then I'll get this alcohol. What's R methyl? And that's how you do it. Again, whenever you see two oxygens on the same carbon, single bonded both to the same carbon, and this in the next case I'll show you are the only places you'll see it. When you react with acid and water, you get back the aldehyde or ketone plus the alcohol you would have used to make that. Whoops. And there's one for you to try. Let me make this hydrant look nicer. I'm at it. There. And it's your turn. What would be the organic product or products for the following reaction? 3 points each. And this reaction, like the two before and next one, are four of the most challenging reactions we'll do this semester. But take a deep breath, let it out. With a little practice, students get it. All right, don't forget to give me a thumbs up when you're done. All right, looks like everybody's done. I better get to work. All right, let's look at this molecule. What's different? Ooh, oxygen, another oxygen. It's the same carbon. This one has a hydrogen, this has carbons. And we got carbons here and here. And what is this? A hemiketal, which you don't have to know the name, but I do, so I'll use it. Let me move this out of the way for me. And now, when you react this with acid and water, which you find in your stomach, keep your eye on the carbon with the two oxygens single bonded to it. That carbon becomes a carbonyl, our prime, or it could be a hydrogen, and our double prime. And then you also get the alcohol you would have used with the aldehyde to make this compound. Now, what's our prime? Ethyl. What's our double prime? Methyl. What's our and propyl? So I can keep my eye on this carbon and becomes this carbon. Excuse me, a slow developing sneeze. It's on the internet for eternity. No, anyways. Now, what's our two carbons? Remember, you don't break carbon, single bonds. Our prime is a methyl. And then what's our, the carbon with on this oxygen is the carbon that will get this hydroxyl group. That's important. If you don't put it there, I'll mark it wrong because that's not what you get. And there you go. There's the molecule you get. Oh, let's do one more. These are fun. And there you go. Have some fun. Dr. White's organic chemistry fun. Give the organic product 3 points each. I see one person done. Two, the rest of you take your time. Anybody else want to give me a thumbs up? Oh, I haven't done this in a while. Well, I think everybody's done, so I better get to work. Now, if we look at this molecule right here, what's different? What's not carbon? What's not hydrogen? Ooh, oxygen here on the same carbon, and they're single bonded to it. One's hydroxyl, one's oxygen with carbons. And then that same carbon right there, I have carbons here and here that are in the ring. Well, I can call that R prime. It could have been a hydrogen, it's not. R double prime. When you have a ring, R prime and R double prime are disconnect together. And when you react that with acid and water, what do you get? Well, keep your eye on this carbon with the two oxygens single bonded to it. It's very rare. This and the next reaction are the only two I know. And you get back the aldehyde or ketone plus the alcohol you would have used to make this compound, which we learned earlier. So here's my carbon, and it's in a ring. So it's ever attached to this carbon, guess what? Comes along for the ride, because you know you don't break carbon-carbon single bonds. Now my general reaction tells me this will be a ketone. And then what's R on the oxygen? And that would be methanol. And that's how you do it. And so this is one of the two key steps. This allows you in your stomach, and I think large intestine or small intestine, one of those two, to break down complex starches or making simple carbohydrates, which we'll talk about later in the semester. And let's move on. Now, this was reversing our acid hydrolysis of a hemiacetal or hemiketal. And turns out if you have reversing of the acetal or ketal or acid hydrolysis of acetal or ketal, the same thing happens. And here again, this is one of the only two places in all of organic chemistry. The previous reaction was one. This is number two, where you have two oxygens, single bond, that's important, to the same carbon. Now, both of those also have R groups on it. And when you react it with acid and water, remember that's what you can get in your stomach, you get back, and if R prime was H, you get back either an aldehyde or ketone you would have used to make that, plus the alcohol. Now I put two here. You don't have to put that there, because on my test I asked, give the organic product or products, not how many. So if you're a lazy organic chemist like I am, I wouldn't put the two there. You don't need it. But if it makes you comfortable and helps you get the right answer, by all means, feel free to do that. Dr. White loves ketones and aldehydes, and I draw one without even thinking. If we look at the following reaction, what's different? Ooh, not one, but two oxygens single bonded to the same carbon. And each carbon you have carbons, R groups. Here you have a hydrogen to the carbon with two oxygens and carbons. My two oxygens with carbons on it to the same carbon. It's got R prime, which could be hydrogen, which it is, and R double prime. And when you react this with acid and water, or water and acid, same thing, keep your eye on this carbon with the two oxygens. It becomes a carbonyl, and what was attached to it, hydrogen or R prime plus R double prime, you get. And then these R groups on the oxygens become an alcohol. Now, what I normally do is, as small as possible, I do the number 2. I put it in quotes only because you don't have to put it there. I ask what are the product or products. You get this aldehyde or ketone, this alcohol. And if you look at the reaction before us, which I'll scroll up, you get the same reaction products. You just don't have to put the 2 there because you don't, but in this one, you don't have to put the 2 either. So whenever you see a carbon with 2 oxygens on it, you're going to get the same products like this. So let's go back up to our original reaction. I'll call this R prime, this R double prime. The carbons on the oxygen, I'll call R. And now I'll look at this carbon and I'll write it. And it'll be this carbon, which is carbonyl, carbon double bond to oxygen. What's R prime? Hydrogen. What's R double prime? Ethyl group. Then my alcohol, what's R? Ethyl. Now, for those who must, you could put the 2 there, but you don't have to. It's funny. A couple semesters has happened. Students have put the 2 there and put the quotes there because Dr. White does it. I must have to do it. No, you don't. But I had these 2, and I think I mentioned it, twins a couple years ago at COD when I was teaching the same course. And if I didn't put that 2 there, they went ballistic. I mean, they got really upset. It was funny. So I don't want upset twins at me. That's double the displeasure. Oh, that was a funny joke. So I put the 2 down there. Your turn. Uh, and why don't you try this one for your fun and enjoyment on this Tuesday afternoon? How do I know it's Tuesday afternoon? Because after class, I got to go get my garbage cans from the front of my house on my driveway because it's garbage day. Tuesday, where I live, is garbage day. While you're doing that, I'm going to sneak off the internet and look up something real quick. Ah, and I found what I was looking for. All right. When you're done, give me a thumbs up. I see one person has. Ooh, another one. I see some more thumbs. So I'll give you another 15.8 seconds. Time's up. Let's do it. Now, if we look at this molecule, what's different? Oxygen's here. Notice there are two oxygens single bonded to the same carbon. Each one has carbons on it. Then on that same carbon, I have carbons here and here. I'll call that R prime and R double prime. Remember, X, R's, and R primes are like X and Y and Z in math. Now, R prime could have been a hydrogen, but it's not. If I react it with acid and water, or water and acid, keep your eye on the carbon that has the two oxygens single bonded. That becomes this carbon. And what was attached to it, R prime, R double prime, or if R prime was hydrogens there, then the R groups on the oxygen become this alcohol. And for those who must, if you have to balance it, go right ahead. I wouldn't, but I'm a lazy organic chemist. So this is R prime. You could call it R double prime, doesn't matter. This is R double prime, and both of these are R. So keep my eye on that carbon with two oxygens. It becomes this. What's attached to it, R prime, is the small R group, and the R double prime is this. So you get this ketone. What's R? 3 carbons, and the carbon bonded to oxygen, this one, which is this one, will have the hydroxyl group. And for those who must, you can put the 2 there. I don't. Actually, I do, but that's so I don't want to get any upset students. And that's how you do it. Now, if I look at the time, this would be a good time to take a break. But let me remind you, don't forget, a week from this Thursday will be test number 2. I hope by Thursday, I better hope, you got to do it, Dr. White. I'll have, just like I did in test 1, I'll have test 2 information up. I can tell you this, on test number 2, it will cover alcohols, it will cover phenol, which is an alcohol, ethers, epoxides, thiols, remember they stink, and also ketones and aldehydes. Unlike test number 1, test number 2 will have more reactions, less nomenclature, because if you notice, I'm spending more time on reactions, because we've already learned the basics of nomenclature, which is why, so there'll be more points on that. And unlike test number 1, where there was 1 synthesis, for test number 2, usually historically I put 3. Any more would be cruel and unusual punishment, which I shouldn't do. And with that, I'm going to say, let's take a break. I'll see you in 5 minutes. Come back at 1:55. I'm going to get up and stretch. Oh no, it's time for me to get back to work. All right, let's get back to work. Everybody back? Let's do one more example of this reaction. And remember, this reaction, I'll teach you later, this one right here, is how your body initially breaks down starches in your stomach. And here's one for you to do. And good news, we're right on track, right on schedule. I was looking at the syllabus. Don't forget, this Wednesday, tomorrow, I'll go through the alcohol problem set. And this Thursday, I'll go through the ethers and epoxides problem set. Don't forget the lab we did yesterday. Distillation is due tomorrow. I see one person done, but I'll wait for everybody else. Please be patient. I try and give everybody time to finish. All right, I think everybody's finished. Let's take a look at this. If we look at this, what's different? Ooh, one, no, two oxygens to the same carbon. And both of those oxygens have R groups on it. And then on that same carbon, I have carbons here and here. I'll call it R prime and R double prime. They're in a ring, so they're connected together, but R prime could have been hydrogen. And when you react it with acid and water, what happens? You get back the ketone or aldehyde you would have used to make that molecule, plus the alcohol you would have used to make that. And for those who must, you can put a 2 there, you don't have to. And now if we go up here, this is R, this is R. This whole ring is my R prime and R double prime. And the carbon with the two oxygens bonded to it, singly bonded, becomes this carbon of a ketone or aldehyde. And everything else, R prime and R double prime, stay attached. So I'm going to keep it attached. Which carbon had the two oxygens? That one. And it will be double bonded to that. And then my R group for my alcohol is an ethyl group. And for those who must, you can put a 2 there. All right. Now, I don't think I've mentioned this, but I was very fortunate. God smiled upon me, not to bring religion into the classroom, but when I went to graduate school, I went to Michigan State. I went there because of one professor. I was able to join his research group after my first year of grad school. He accepted me, and that was Dr. William Roosh. Now, Dr. William Roosh got his PhD from Columbia, from the great organic chemist. Dr. Roosh was a very good organic, but the great organic chemist, Gilbert Stork. So I guess he's sort of my grand advisor, Gilbert Stork. And one of the things he's known for is the following. Now, what if, like today, you were going from a building, if we were at ECC, to your car in the parking lot, and it's raining, and you don't want to get wet. Or say you're in your car and you're going to come into the building and you don't want to get wet. What do? Well, you either have a raincoat on or you have an umbrella to protect you. Well, some reactions we have with ketones and aldehydes, or I should say with other functional groups in a molecule with ketones and aldehydes, those reagents would also react with the ketones and aldehydes, and you don't want that to happen. So what Gilbert Stork, Dr. Stork, invented, I like better than discovered, he created, was a way of putting on what's called a protecting group. Just like you put on a raincoat to protect you from the rain, and then when you get in, you take it off. He found a way of protecting aldehydes and ketones in a certain reaction. And then when you're done with that reaction, you can take that protecting group off. What is that? Let's take a look. Now, the reaction he came up with was if you take a ketone or aldehyde and react it with ethylene glycol, what reaction do you get? Well, this is a ketone or aldehyde. If we look at this, what this really is two alcohols. They're in the same molecule, but they react as two alcohols. And you just learn I have a ketone or aldehyde, I react it with two alcohols. What do I get? This acetal or ketal. And you learn that if I add water and acid, I can, oops, hold on. That's better. I go back to this and this. So what happens here? What's R here and here? Keep your eye on the carbonyl carbon like here. And what's attached to this carbon, R prime or hydrogen, will be still attached. I have my two oxygens. And what's R prime and R groups? CH2. But do you break carbon-carbon single bonds? No. And this bond is still there. And when you have two of the same functional groups in the same molecule, the reaction goes much better because the second alcohol is what we call intramolecular in the same reaction. Now, for some reason, students forget to put that bond. I don't know why, but they do. Don't you do that because you won't have four bonds to those CH2 groups. Let's try this out. And this is just like putting a raincoat on a ketone or aldehyde. So if we look at this reaction, what's different? Ooh, carbonyl with hydrogen carbons, that's an aldehyde. Could have been a ketone. Ooh, let's look at this. One hydroxy group on carbon, two hydroxy groups on carbon. That's two alcohols. Oops, didn't give myself enough room. Two alcohols, but they're connected together. Acid catalyst, keep your eye on the carbonyl carbon. What's attached to it? R prime and hydrogen, R double prime is still there. Oxygen, oxygen, R, R. Well, in this case, what's R? This. What's our prime? That hydrogen. What's our double prime? That methyl. So let's put this all together. Keep an eye on that carbon. I'll do that first. What's attached to it? Our primer hydrogen. Our double prime is still attached to it. Then I have my two oxygens, and now R is CH2. But do you break carbon-carbon single bonds? No. So this bond is still there. And again, I don't know why students forget to put that. And if you forget to put that, that's wrong. But this is a way of putting on this very special protecting group that you can take off by just adding acid and water, and you go back to your aldehyde and ketone and ethylene glycol, which I can take off very easily with water. So it's quite a nice reaction. I forgot what award he won for that. Oh, I haven't used this in ages. That means new stuff, end of it, and new stuff. But anyways, let's try one. And I'll never give a synthesis for this reaction. Your turn. What would be the organic product or products for the following? I see one person done. Take your time. All right, I think everybody's done, so I better get to work. So the question is, what's the organic product or products you're following? If I look at the first molecule, what's different? Oxygen, it's double bonded to carbon. And on that carbons, I have our prime and our double prime. I have a ketone, could have been an aldehyde, but it's not. Then over here, hydroxyl group on carbon, alcohol, two of them in the same molecule. Two alcohols, acid catalyst. Keep your eye on the carbonyl carbon. What's attached to it? Our prime and our double prime are still attached. Then I have my oxygens to this carbon and are on the oxygens. Well, what's our prime? Methyl. What's our double prime? Methyl. What's our each one of these CH2s? So if I keep my eye on this carbon, I'll write it up here. What's attached to it? Our prime, methyl. Our double prime, methyl, oxygen, oxygen, CH2, R group, CH2, R group. But don't forget this bond is still there. And that's how you do it. Now, the beauty of this is I put on my protecting group, and you do a lot of this work was done for research in which I didn't do, but my boss did, Dr. Rouge, when he was a grad student, with steroids. And I'll talk about later steroids, if you don't know, are your hormones. And this helps synthesize certain steroids. Now, when I want my ketone or aldehyde back, all I do is add acid and water. And that's the beauty of it. It's a protecting group. And I thought I'd teach you that. And these four reactions, formation of hemiacetal, hemiketal, formation of acetal or ketals, reversing the hemiacetal or acid hydrolysis of hemiacetal, hemiketal. I've got to change this to acid hydrolysis, sounds better. But I never ask you names of reactions, and acid hydrolysis reversing the acetal ketal. Those four I will never put on a test or the final synthesis, give the starting materials. I will put on, give the product or products like we just did. And let's move forward. All right. Whoa. This is very special time for Dr. White. Does everybody see on your screen right now? Let's see if I got it there. Yes, you should. You see Victor Grignard in a picture, a guy with a great mustache. I wish I could have a mustache like that, but with a gas mask and other things, I can't. But anyways, Victor Grignard is one of my heroes of organic chemistry. He's one of the great organic chemists of all time, one of the great French organic chemists. And he won the Nobel Prize for some of what I'm going to teach you. And what Victor Grignard did was he created or invented, first of all, something called the Grignard reagent in honor of his work. And then he used that reagent to do something very special, very rare, make a carbon-carbon single bond. And we call that the Grignard reaction. And I'll teach you that. And in graduate school, I used those reactions to make certain molecules I needed for my research. And without that, I don't know how I would have made those molecules. And therefore, I'm forever grateful to him and always in awe. That's why I call him my hero. And let's look at the Grignard reagent. Now, the Grignard reagent is a simple reaction. You take an alkyl halide and react it with magnesium. It's quick, it's fun. I'm happy about it. I'm having a good time. X here, I forgot to put on here, is chlorine, bromine, or iodine. And this is called RMGX, and it's important the order you put that. The carbons in R is bonded to magnesium, which is bonded to the halogen. And it's called in honor of Victor Grignard, the Grignard reagent. And let's do some practice. And the question would be, what's the organic product or products of the following reaction? And we look, what's different? What's not carbon? What's not hydrogen? Ooh, look, a bromine on a carbon, alkyl halide. X can be chlorine, bromine, or iodine. Ooh, magnesium metal. That's different. And what do you get? You get the Grignard reagent. The carbon that the halogen is on is the carbon the magnesium is bonded to. The carbon that the halogen is on is the carbon the magnesium is bonded to. All right, if we look up here, that's my R group. Do you break carbon-carbon single bonds? No. So I'll have 4 carbons. Which carbon has my halogen? This one. So I'll be bonded to the magnesium, and bonded to that magnesium will be my bromine. And I can put in my hydrogens. And that's how you make a Grignard reagent. Now, watch closely. Common mistake students make, which is why I'm telling you, is this. This is wrong. There's no such thing as in nature or in chemistry that exists with a carbon bond to bromine and magnesium bonded to that bromine. This is wrong. No, it's this way. The magnesium is on the carbon, the bromine on the magnesium. Please make sure you get that right, or I'll mark it wrong every day of the week and weekend too. So let's have some fun. Oops. And there's some fun. What would be the organic product or product of the following? Now we're getting into the really good stuff, and I am happy. Told you I'd have a lot of fun this chapter. Well, I see a couple people done. All right, I think everybody's done. Let's look at what's different. What's not carbon, what's not high. Ooh, iodine on the carbon, alkyl halide, magnesium. The Grignard reagent reaction, making a Grignard reagent. And here, don't forget, X can be chlorine, bromine, or in our case, iodine. And what do you get? The Grignard reagent. What's our this? Do you break carbon-carbon single bonds? No. So I have 3 carbons across, one here, methyl. Which carbon has the halogen? This one. And you get magnesium iodine. And that's the 2 there. And that's how you make the green. Oh, let's have some more fun with this. I'm in a great mood. Let's do a synthesis one. What would you react with magnesium to make that compound? And this is the fun part of organic chemistry, figuring out how to make things. Because that way you can make money, help people, save lives, and do a lot of things. If you think about it, the people who made some of the vaccines, that was really organic chemistry, but a very specialized one. And they were saying, how do I make this molecule to help save lives? And they did. And I hope public service announcement from Dr. White, if you haven't gotten your 2 shots yet, please do. It will help save your life. I got mine, and by the way, in the past, I react very badly to vaccines and vaccinations, but the Pfizer, either both shots, other than for an hour or 2, a little sore muscles in my arm, it was nothing other than it will hopefully save my life and keep other people around me healthy too. I still wear my mask because I'm still gun shy. All right, anybody need more time? Everybody done? There's a thumbs up button where I see it works. All right, let's look at how do you do this. We're going to look at here what's the, magnesium chloride, that's different, on a carbon. And what do we have? We have the Grignard reagent. Remember, X can be, in this case, it is chlorine, bromine, or iodine. And how do you make the Grignard reagent? You react magnesium plus the alkyl halide, X, Rx. And now, what's my R group? This. Therefore, that's what we're going to start with. The carbon to magnesium chloride is on, or halide, the Grignard reagent, is the carbon the halogen started with. What's our halogen? Chlorine. And therefore, that's how you make that molecule. And that's the fun part of organic chemistry, figuring out how to make molecules. Now, you know how to make the Grignard reagent. So what? Well, so what is the following reaction, which is wonderful reaction? And that's what helped Victor, hold on. Yep. Let me do something every once in a while after a long day. What I'm doing is cleaning out some files that lock up my computer for this. And now we're back on track. Sorry about that, but and why is this important? Because of the following reaction, the Grignard reaction. Let me just do one thing. All right, the Grignard reaction is a two-step reaction. And one of the things I haven't shown you, and before I show you this, let me talk about something that's standard in organic chemistry, because we're lazy. If I have A, and I'm going to do two sequential reactions with it, say reactor with B, and second step we reactor with C to make D, I could have written it this way. A and B react to make something, what reacts with C to make D, but this is a lot of work. And organic chemists are lazy. So what this means is A reacts with this first reaction, 1, which in this case B, then a separate reaction, but usually in the same round bottom, or we say pot. You react it then with C, and then you make the product D. So this is a shorthand for showing A reacting first with B, then C to make this product D.
Hey, Dr. White, is your whiteboard supposed to be on or?
Am I, oh, guess what? So I forgot. Let's try, now do you see it? Thank
Yeah.
you for letting me know. All right, let's do that again. By the way, can you see I'm blushing? Not really. But anyways, I am feeling a little foolish, but Zoom does that. Zoom was telling me you saw it. That's why I use my thumbs up people thing, because I think you should see it. You don't. All right, let's do this again. If I have a reaction A plus B, and then whatever I make, I react with C to make D. So it's actually one reaction and a second one right after it. An easier way to write it is this way. A reacts with B first, and then second step, second reaction with C to make D. And organic chemists being lazy, we prefer this way. And I'll be doing that a lot the rest of the semester because that's this traditional lazy way of doing it. All right, let's look at the Grignard reaction. Thumbs up, people. Do you see it on your screen? Thank you. Now, if you take a ketone or aldehyde and R prime, if it's Hydrogen is a ketone. If it's carbon, it's an aldehyde. And you react at first with a Grignard reagent, which I'm going to call our triple prime. That's just like X, Y, and Z. And second step, acid and water, you get this new molecule. And what's special is you've made a carbon-carbon single bond between this carbon right here and the carbon on the R triple prime with the Grignard, and you make an alcohol. And being able to make carbon-carbon single bonds is very special, very rare. There's only a handful of reactions. This is one of them, which is why Victor Grignard won the Nobel Prize for this, first uh, coming up with the concept of making the reagent and showing how it's useful. Let's have some fun with the Grignard reagent. Oh yeah, we're gonna have some good fun. Now, if our triple prime is very large, I might put it in front, but yeah, I can put the S, H plus water, water H plus. And the question is, what's the organic product or product you get here? And look, what's different here? Oh, it's a ketone. Carbonyl, carbon double bond oxygen. And our prime is this, but it could have been a hydrogen, that would have been aldehyde. And here's,
Dr. White, your whiteboard's not on again.
it's, how did I do it again? It tells me you should see this. All right, now do you see it?
Yeah.
All right, hold on. I'm gonna have to reboot my brain. Let's try it again. See, I got so excited with this reaction. Something went wrong. I did wrong. But anyways, I'll try and calm down. You start out this reaction with this reagent, second step, water and acid. What's different here? Carbon double bond to oxygen, carbons here and here, and that's a ketone. And if it's hydrogen, it would be an aldehyde. This methyl group is R prime. This other methyl group is our double prime. Now, what are we reacting the first step? Carbon, carbon, oh, magnesium halide, a Grignard. I don't know why I didn't call it, well, you've already got single and double. I could have called it R, but I like calling it on triple prime. And second step, acid and water, water and acid. What's attached to the carbonyl is still attached. Carbonyl carbon, remember carbon double bond to oxygen. And now this opens up to an alcohol and you do that special thing. You make a carbon-carbon single bond from the Grignard to what was the carbonyl carbon. And what's our R triple prime? Ethyl. So let's construct it. My carbonyl carbon is this carbon. What's attached to it? R prime or hydrogen, methyl. What's also attached to it? Methyl. And then hydroxyl group, and then no oxygen between this R group like we did earlier, directly bonded. And here's the organic synthetic organic. From two very simple molecules, I've made a very complex molecule. And that's always a good thing. And that's how a Grignard reagent works, reacts with a ketone or aldehyde. And this reaction, I will never give as a synthesis. I know how to do it, but I don't think that would be fair. So I won't. But I will ask you give the organic product or products for the following. And when you're done, don't forget, give a thumbs up. All right, anybody need more time? I guess not. Let's take a look. What's different here? Oxygen, double bond, the carbon, carbonyl. It's got a hydrogen. It could have been an R group. And over here, we've got carbons, R double prime. We've got an aldehyde. What a reactant in the first step. What's different? Oh, magnesium chloride on a carbon, R triple prime, MgX. As to Grignard, remember X can be chlorine, bromine, or iodine. Second step, water and acid or acid and water. I write them both ways. Keep your eye on the carbonyl carbon. What's attached to that is still attached. This opens up to an alcohol, and then this forms that special thing, a carbon-carbon single bond. So what's my R prime? Hydrogen. R double prime? Ethyl. R triple prime? Methyl. And if I keep my eye on the carbonyl carbon, I'll write that first. What's attached to it? Hydrogen. R double prime? Ethyl. Hydroxyl group. And then that special thing, carbon-carbon single bond, and our triple prime is a methyl. Oh, I've got to do one more of these. I am having fun. And there you go. What would be the organic product or products for the following? And don't forget, give a thumb. Oh, I know what I can do. Well, it looks like just about everybody's done, so I'm going to get going. And if we look at the first molecule, what's different? Ooh, oxygen double bond to carbon, carbonyl. I've got carbons here and here. This is a ketone, a cyclic, could have been an aldehyde. And a cyclic ketone, remember R prime and R double prime are bond together. What's going on here? Ooh, what's different? Magnesium halide on a carbon, that's a Grignard. Remember, X can be chlorine, bromine, or in our case, iodine. And second step, acid and water, or water and acid. Keep your eye on the carbonyl carbon. What's attached to that is still attached. Our prime and our double prime, that carbon becomes an alcohol, and then you do that special thing. You make a carbon-carbon single bond from the Grignard reagent, our triple prime. Well, what's our prime and our double prime? The ring. Here's that carbon right here. It'll have an alcohol, and that carbon will have the carbon with the Grignard. This is my R triple prime, will be the carbon bond to the carbon right here. And that's this molecule. And the question is, why did I pick that example? Because a year or two ago, I picked it and I looked at that and it said, as a synthetic organic chemist, how would I make that without the Grignard reagent? And I haven't found an easy way to do it. I could do it very complex way, which wouldn't be good. But with a Grignard, it's easy, it's fun, and it's nice. Now, what I'm going to do is take a little side trip in case you wonder, how does synthetic organic chemists think? Well, if I had to make this, I'd need this, which I can buy, and this I can buy, but what if I couldn't? How would I make that? Well, you learn. And this won't ever be on the test. Take alkyl halide plus magnesium, and I could also have the iodide. And how would I make this? One way is isopropyl alcohol plus either HX or thionyl chloride. And if I didn't want the chloride, if I wanted the iodine, I would react it with HI. And that's how synthetic organic chemists, you like chess game, you try and move backwards a couple of moves to how do I do all that? And that's what I've been trained to do. But on the test, take a deep breath, you just have to know this reaction. And that's the Grignard reagent. Oh, by the way, one of the things I did was take an aldehyde and make it into alcohol, secondary alcohol, which I oxidized to make the ketone I needed. And you can take these alcohols and react them further. So that's the beauty, and it truly is beautiful, of the Grignard reaction. All right, let's move on. Now, Dr. White's got a big smile on his face. I do. Now, if we look at a ketone or aldehyde, let's look at the carbonyl. Carbonyl, carbon double bond to oxygen. Does everybody see hydrogenation on your screen? Thank you. And that double bond has one pi bond and one sigma bond. And you learned about pi bonds in carbon-carbon double bonds if you add hydrogen and a catalyst. And the cat I didn't put down here, but I should have, bad Dr. White. Nickel, platinum, or palladium. And what do? You break the pi bond, and each atom of the double bond, in this case carbon and oxygen, gets a hydrogen. And this is called the reduction. That's a way of taking a ketone or aldehyde and making an alcohol if you need one. And I'll show you later on where this reaction helps make an interesting ingredient in many over-the-counter drugs that you can purchase. And if we look at the following reaction, anybody getting nightmares hearing me say what's different? What's not carbon? What's not hydrogen? What's not a carbon-carbon single bond? And actually, every time I look at a molecule, I look for all those functional groups. And the way I'm telling you is an easy way to remember that. Oh, look, we have a carbon double bond oxygen, and it's an aldehyde, hydrogen, but this could be R prime, aldehyde or ketone, R double prime, and react it with hydrogen and a catalyst, and the catalyst equals nickel, platinum, or palladium. In this case, we're doing platinum, and you break the pi bond, and each atom of that double bond gets a hydrogen. So what's R prime, hydrogen? What's R double prime, ethyl? That will still be bonded to this carbon. So I'll do that. And then I broke the pi bond and each one, and you make that alcohol. And that's a way of making one propanol. Not the more complex reactions, this makes a difference. So we've got time. And I can write this a little differently. Let's see if you can handle it. And what would be the organic product or product for a following reaction? 3 points each. Don't forget, tomorrow I will be going through the alcohols problem set. Make sure you try it before I do. I see one person done, two. Everybody else done? Looks it. I better get to work. All right, what's different in this molecule? Ooh, oxygen double bond to carbon. That's a ketone because I have carbons here, carbons here. And I just drew it a little differently, but it's still a ketone. And what am I reacting with? Hydrogen and a catalyst. Catalyst can be nickel, which in this case it is, platinum, or palladium. And what happens? You break the pi bond, and each atom of the double bond gets a hydrogen. What's attached to the carbonyl stays attached, R prime or H, and R double prime. And therefore, what's R prime? This. What's R double prime? That. Here's my carbonyl. I'll do that first. R prime methyl, R double prime, 3 carbons. Break the carbon oxygen pi bond, and each atom gets a hydrogen. And you make that alcohol. And that's how you do it. And if I look at the clock, it's time to take a break. I'll see you in 5 minutes, and we'll continue on. I haven't used this in a while. Let's get back to work, everybody. And we're talking about hydrogenation of a ketone or aldehyde. And let's have some fun. Remember, on test number 2, I'll have about 3 synthesis problems. So let's do one. What would I react with hydrogen and a catalyst, palladium, to make that molecule? Give the starting material, which I show by a question mark. All right, I think everybody's done. Let's take a look at this. Well, how do you figure out what to do? Well, you look at what you're trying to make and what's different. Well, here we have an alcohol, which I could write it that way, but I could also write it this way. And why am I doing that? Because I see hydrogen and a catalyst. And I know the catalyst, first of all, can be nickel, platinum, or in our case, palladium. And what do you start with? A ketone or an aldehyde. Now here I have carbon, here's the carbon with the hydroxyl group. I have carbons here and here, so this is a ketone. And I call that R prime and R double prime here, but they're connected together in the ring. So that means I start with a ring because I don't break carbon-carbon single bonds. And the carbon with the hydroxyl group was the carbon double bond to oxygen. And that's how you do it. Okay, everybody up to speed. Now, I'm going to write something on the whiteboard. You do not have to write this down. It's to illustrate a point for the next reaction. So let's look at the whiteboard. What if you had this molecule, and again, don't write this down, and you wanted to take it to make this molecule? And you look at this and say, oh, I've got an aldehyde. I want to make it into an alcohol. I'll use hydrogen and a catalyst, say nickel. And you know what you get? A mess. Why? Because what do we have here? Double bond. And you learn that double bonds with hydrogen and a catalyst we'll do this. Ketones and aldehydes. With a catalyst and hydrogen, we'll do this. And this is a non-selective reaction. Therefore, both of these are a mixture, one or the other, all three. You could get where this is no longer here. This is still an aldehyde right here. You get it where you lose this double bond. So it would be like this. Plus you get the alcohol, or it may be an aldehyde. You get a mess. And when you're trying to make a specific molecule, you don't want a mess. They're not fun to deal with and they're not economically feasible. So what do we do? Well, it turned out that kind of problem existed in the end of World War II, or near the end in the last year or two of World War II. One of the things that was quite amazing from World War II was the fact that because the Americans and the Allies, English, our main, and the Russians too, but the English and the Americans couldn't get raw materials because they were blocked off from Germany or Japan from things from Asian basin, so to speak. They had to figure out, how do we get these raw materials? Well, you synthesize them. And there was a tremendous expansion of the knowledge of organic chemistry to support the war effort. And one of those people who made a tremendous advancement was the great American chemist, H.C. Brown. Dr. Brown, who taught at Purdue, came up with the following reaction. And also invented two reagents, which he did win the Nobel Prize for. And that is lithium aluminum hydride. Lithium aluminum hydride is Li, lithium, Al, aluminum, with 4 hydrogens. And think of this as like our H minus, a nucleophile, or another way of thinking of it, think of the H minus as like the R triple prime in a Grignard. What's different? If you take a ketone or aldehyde, and react it with first step, lithium aluminum hydride, second step, acid and water. I have a comma here. I could have put a /2. And now you do the same thing you do with hydrogenation of a ketone or aldehyde. Each atom of the double bond gets a hydrogen. Now, the thing is, lithium aluminum hydride is very selective. It will only react with carbonyl compounds, ketones and aldehydes. It will not react with carbon-carbon double bonds, which is what we want. So that's the beauty of this reagent, and also why he won the Nobel Prize. He also did another one, which is similar, which is called sodium borohydride, NaBH4, same type of reaction, but less, I think it's less expensive, I'm not sure. But anyways, and that combined with this, but I'm only going to teach you lithium aluminum hydride. Thumbs up, people. Can you see my whiteboard? Thank you. And if we look at the following reaction, what do we have that's different? Carbon double bond to oxygen with carbons here and here, ketone. But it
We
could have
can
been,
see the whiteboard, but we can't see what you wrote.
uh-oh. Now can you see it?
No.
Hold on.
It's just the blank whiteboard.
All right, now do you see
There.
it?
Yes, yes.
I don't know what happened. Uh, whoa, let me try something. That's weird. It was on my screen, now it disappeared. All right, let's do it again. You start with this molecule and react with lithium aluminum hydride. Second step, acid and water, water and acid. What's this? Thank you for whoever let me know. Was that Johanna who let me know? Thank you. Or whoever else did, thank you. If you have a what's different, carbon, double bond to oxygen, carbon's here, carbon's here. This is a ketone. It could have been an aldehyde. What are you reacting with? Lithium, aluminum, hydride, LiAlH4. Second step, water and acid, or acid and water. And what's attached to the carbonyl is still attached. And then you break the pi bond, and each atom gets a hydrogen. And it's just like if we're hydrogenating, but this reagent will only attack carbonyls, won't react with carbon-carbon double bonds. So what's our prime? Ethyl. What's our double prime? Methyl. Keep your eye on the carbonyl carbon. What's attached to it is still attached to it. My ethyl group, R prime, and my methyl group, and you break this to do that, and that's how you do it. And now it's your turn. And have fun. This is H plus. Remember, H plus is acid. Something like sulfuric acid would do the trick. Don't forget the lab we did yesterday is due tomorrow. I see one person done. Another one. I think everybody's done. Let's take a look at this. What's different? Oxygen, bond to carbonyl. It's got a hydrogen alkyl group. It's an aldehyde, but it could have been a ketone too. In this case, our prime is H, our double prime, reacting with lithium aluminum hydride. And second step, acid and water. And what you do, what's attached to the carbonyl carbon is still attached. And then you break the pi bond, and each atom of the carbon-oxygen double bond gets the hydrogen. What's our prime? Hydrogen. What's our double prime? Isopropyl. That's attached to this carbon. It opens up, you break the pi bond, and each one gets a hydrogen. Oh, this is fun. And Dr. White's used this reagent to make alcohols from ketones and aldehydes in graduate school. In industry, I worked in other industries that doesn't use this. Lithium aluminum hydride is used in the pharmaceutical industry. And what would you react with lithium aluminum hydride, water, and acid to make the following compound? And when you're done, don't forget to do the thumbs up. Everybody's done. I can get to work. I'm so proud of you people. Think about it. 6 months ago, if I had shown you this and said that, would you understand even what I'm talking about? Think about how much you've learned in my class. You should be very proud. All right, let's take a look. What's different? Ooh, carbon with a hydroxyl group, and each one has a hydrogen sticking up, or we have an alcohol. And I'm writing it this way because as soon as I see lithium aluminum hydride, I think of ketones and aldehydes. And on here, we would have our prime or hydrogen and our double prime. And what do we start with? An aldehyde or a ketone. And if we look at this, this is my R group, because this carbon with the hydroxyl group, hydrogen with the oxygen, is this carbon. And it also has this. So I'll come back here and say my carbon bonded to the oxygen is now this carbon, which is part of the carbonyl. And attached to that is R, methyl, and R prime. If you take this ketone, react it with lithium aluminum hydride, water, and acid, you will make that alcohol. And by the way, that's a pretty complex molecule, and you did it. Hopefully you feel good. Everybody, feel good. That's an order from Dr. No. Anyways, it's silly statement Tuesday. All right, let's get back to. All right, everybody see oxidation of carbonyl compounds? Put a cross through that. We're going to cover that next chapter, not this one. I should have taken it out. Everybody's smiling. All right. I have to warn you about something. If the next couple of slides, Dr. White, looks like I'm having way too much fun, I am. Also, the next couple of slides, till I turn it back on, click, the switch will be off. Will this be on a test? But it's important background information for you to understand what's going on when the switch will be back on. Now, it turns out there's something called the tautomerism. That's when you only move electrons and a hydrogen. And aldehydes and ketones, they form the keto-enol tautomerism. And that's because aldehydes and ketones, remember, switch is off right now. This won't be on a test, may exist in equilibrium of two forms. One is called the keto form, the other enol. See board. I better get to work. Everybody see the whiteboard now? That's clear. Thank you. Now, for ketone or aldehyde, and this is a terminology I'll use, The carbon bonded to the carbonyl carbon is called the alpha carbon. The carbon bonded to the carbonyl carbon in a ketone and aldehyde is called the alpha carbon. And this is in equilibrium with the following. I can move electrons and a hydrogen to make this new molecule. Now, this is called the keto form, even if it's an aldehyde. And this has a double bond. Remember, that has the E on the ending, and an alcohol that has the OL. And chemists said, all right, let's call that enol. Just drop the extra E. And this is called the enol form. And this is in equilibrium, and it goes back and forth. And because this happens, it makes something special happen on the alpha carbon. Again, alpha carbon, carbon double or bonded to the carbonyl carbon. And let's look at what's that special thing. Now, it turns out the alpha hydrogens, the hydrogens on the alpha carbon in a carbonyl carbon, are very acidic. Millions of times, I don't know about millions, quite much more acidic than, say, a carbon on an alkane, just CH3, CH2, that type. And this is due to resin stabilization of what's called the enolate anion. Ooh, Dr. White's now really smiling. See board. Remember, switch is still click off. If we consider the following again, the alpha carbon, these hydrogens I can remove or are in equilibrium. This is acidic. I can take it off with a base to form the enolate anion. If you lose a H plus, that will be an anion. And remember, this is the, and if you had like a sodium base, you'd have a cation here. I'm not showing it. And this is called the enolate anion. And it comes from the name enol, enolate meaning that kind of anion. My PhD thesis dealt with a very special type of enolate anion, and I'm a world authority in enolate anions. And this will never be on test, but it brings back good memories. My PhD thesis dealt with kinetically favored cross-conjugated enolate anions. And most organic chemists would, unless you specialize in enolate anions, which many don't, wouldn't have a clue what I just said, but it brings back good memories. Now, why is the enolate anion stable compared to if you just had ethane? Why can't you pull a hydrogen off ethane to form an anion? Because I can draw another resonance form. Moving electrons, this goes here, and use a double-headed arrow, just like in benzene. Oop. And this would be the other form of the enolate anion. There are two resonance forms. And because it can form these two, it's stable. And therefore, when pulling this off, it's stable. Now, if you take something like this, it's not going to do that because this molecule is extremely unstable. I've made some of these for something, but when you get a negative charge on carbon that can't be stabilized by resonance stabilization, this is really nasty stuff, but it's hard to do. This is easy to do. Now, why am I talking about this? Because enolate anions are nucleophiles. They tack things with a positive charge. And by the way, I should have mentioned the Grignard reagent is a nucleophile. It attacks the carbonyl carbon and bonds to it. So enolate anions allow you to do something very special. Make a carbon-carbon single bond, something very rare, very special. And now the switch is on. The following is the aldol condensation. And what happens is, and I'm writing it in a way which will help you learn it, you have, and we'll just, instead of doing ketones and aldehydes, I'll stick with aldehydes because that makes it. And sometimes you'll have a solvent like water or something else. And here, this is the alpha carbon. And this is a base. If this is acidic, you can remove it with the base. Now, Dr. White's going to have way too much fun. I'm going to show a mechanism to help you understand what's going on. It will never be on a test, but come on, I'm an enolate chemist. Me not do a mechanism of an enolate reaction? No way. But it's time for me to have fun. Everybody see the whiteboard? On a test, an organic chemist at my level, we would never write it twice, but there are other bases, but for this class, I'll stick to sodium hydroxide. Now, the alpha carbon has acidic protons. And you pull one off to form the enolate anion. Now, this enolate anion is very reactive. And what's around this more of itself? And this attacks that and opens it up like a Grignard. And what happens is the first aldehyde is there. It bonds to the carbonyl carbon. This opens it up, and this becomes, because you're in water, an alcohol. And what's attached to this, CH2R, is still attached to it. And you've made that carbon-carbon single bond from the alpha carbon of one aldehyde to the carbonyl carbon of the other. And this allows you to make very complex molecules from very simple ones. Now, I did some very other enolate chemistry, which I'm not teaching you. There are other things enolate anions can react with to make carbon-carbon single bonds, but for this class, because we only have 16 weeks, and even though I would like to cover that, I think for you people, it's more important to learn more about fats and oils, carbohydrates, and proteins. So let's take a look at this in action. My gift to you is, normally organic chemists would write one aldehyde and sodium hydroxide and water, and everybody know there are two of them there, but on a test, I will do this. Also, this reaction, I'll never give you synthesis. And the question is, what would be the product or products? If we look here, oh, an aldehyde. And I'll write it this way. Ooh, the same aldehyde. Well, I'll write it again. Base and water. That means the alpha carbon of the first aldehyde, you'll lose the hydrogen, and it will attack the carbonyl carbon of the second one. And the first aldehyde, I've lost the hydrogen to base to form the enolate anion. It bonds to the second one. And what's attached to that? CH2, CH2R. So this is my R group. I'm going to write the first part here because this one, I'm going to lose the hydrogen from that, and it's going to attack here. Remember, there's only 4 bonds to carbon. Here's my alpha carbon, the carbon attached to the carbonyl. It will bond to this carbon right here, open it up to an alcohol, and it's called a Aldol condensation, Ald for aldehyde, Al for alcohol, OL. And I'll have CH2 and my R group, which is ethyl. And that's how you do. Notice I've made a very complex molecule because I made that special thing, a carbon-carbon single bond. And now it's your turn to have fun. Have fun. What would be the organic product or product for the following? Yeah, I should say, for those of you watching this out in YouTube world, hi. That was awful. I see one person, Dawn. Thank you, Kendall. And 2, John is down. I shouldn't use names. I'll wait for the other 2 to finish up. Take your time. Everybody's done, so I better get to work. Now, oh, I've got base. Oh, by the way, here's the giveaway. I've got 2 of the same aldehyde, aldol condensation. Shh, don't tell anybody, I'm being nice. And you take a hydrogen off the alpha carbon. I'll do that. And the enolate anion attacks the carbonyl carbon of the second aldehyde, opens it up to an alcohol. What was attached to that, notice here's my R, but you could also do it the way I'm parsing it. And that's the molecule you have. And since there won't be any synthesis, that's all the examples other than when we do the ketone aldehyde practice problems I'm going to do now. Oh no, everybody see, we've come to the end of the chapter, but not the end of our meeting together. First of all, I have covered everything that will be on test number 2 a week from this Thursday. So this gives you plenty of time to practice for that. However, I'm going to continue on. So you know what that means? It's new functional group and new chapter time. And this new chapter will be on test number 3, not test number 2. But I'm going to use the time we have because we're going to lose some time on Monday because of the holiday for July 4th, which you have July 5th off. So let me open that new chapter. All right, thumbs up, people, help me out. Do you see chapter 10, carboxylic acids and their derivatives on the screen? Thank you. All right, this chapter again will be on test number 3, but in the summer we move along. And guess what? In the fall and winter, I do similar. All right, coming attractions in this chapter. We're going to talk about something that's pretty sour. I'm also going to talk about something in this chapter that smells really good, tastes really good. And then, I'm going to talk about the very first chemical reaction I ever did with my hands when I was way little and young. Well, also, I will give you my father's secret recipe. It's a secret how to make the best spaghetti sauce, which you can use if you ever have to cook spaghetti sauce for a lot of people or just yourself. So there's a lot to do, and let's get going. This chapter deals with carboxylic acids and their derivatives. What's a derivative? Something that's made from a functional group. So we're going to talk about carboxylic acids and new functional groups that we make from carboxylic acid. What's a carboxylic acid? Good question. It's a new functional group. Now this one contains a carbonyl, carbon double bond to oxygen, and on that carbonyl, you have a hydroxyl group also, and it's called a carboxylic acid. And the general formula for carboxylic acid, I have written there, my software does that, but R group, carbonyl, and a hydroxyl group. This is a carboxylic acid. And we use carboxylic acids in our daily life, and I'll talk more about it this semester and this chapter and other chapters. So this is a carboxylic acid. Now, another way you can write it is this way and this way. I almost never ever do it this way. I do sometimes later in the semester do that way. And I should warn you, when I was at industry at one company, we made synthesized carboxylic acids. So I'm an expert in this area, certain types of carboxylic acids. I worked in a couple different areas of organic chemistry. Oh, come on. Now the question is, how do you name a carboxylic acid? And I'll show you. You find the longest chain, which contains the carbonyl carbon, the carbon double bond carbon of the carboxylic acid. Find the longest chain and name it as an alkane, which you've learned 1 through 10. You drop the E at the end of the A and E, and you add the letters OIC and the word acid. Again, I'll show you this. You drop the letter E at the end of the alkane name, and then you name it at OIC in the word acid. Now, just like an aldehyde, the carbonyl carbon double bond to oxygen of the carboxylic acid is always carbon number 1. And then the name and number of all other substituents, as you've learned. Now, number 5, I'll never ask on a test, or the final, but carboxylic acid group attached to a ring, the ending is called the carboxylic acid. So something like cyclohexane carboxylic acid, but I've never encountered those. I've done others where you use the rules up above. So let's get to work. Give me a break. Hold on. Time out while I close something. Let me try something else to help us out. What I just used, if you're not familiar with the product CCleaner, you should have it on a PC. I don't know about a Mac. And let's see if I can get things going again. All right. On this PC, besides a tablet, a webcam, and Zoom in Word, it sometimes gets confused. All right. Everybody see my whiteboard now? Thumbs up, people. Thank you. All right. We're talking about carboxylic acids. And let's look at one. And if we look, what's different? Oxygen there, double bonds as carbon. Hydroxyl group, single bonds as same carbon. This is a carboxylic acid. How do you name it? Find the longest chain with the carbonyl carbon. That's 1, 2, 3. That's propane. Drop the E, add OIC, and the word acid. And no number, because the carbonyl carbon is always number 1, and that's propanoic acid. And that's how you do it. And I'll do one more, and then I'm going to let you have a chance. If we look at this molecule, look for what's different. Carbonyl carbon with an oxygen double bond, hydroxyl group, R group, and this is a carboxylic acid. And how do you name it? You find the longest chain with the carbonyl carbon. 1, 2, 3, 4, 5, 6, or I could have called this one 6. You get the same answer. 6 is hexane. Drop the E because it's a carboxylic acid. Add the letters OIC and the word acid. Are we done? No. Because as soon as we say hexanoic acid, we have Oh, look, a methyl group. And where is it? It's on carbon 5. And that's how you do that. And let me give you have one. And there's one for you to try. Give the IUPAC name for the following. 3 points each. Remember, drop the E, add OIC in the word acid. And the carbonyl carbon of a carboxylic acid, like an aldehyde, is always number 1. And this is going to be on test 3, not test 2. See one person done. Don't forget, give me a thumbs up. 2, 3. I think everybody's done, so I'm going to get to work. What's different? Carbonyl. Same carbon has a hydroxyl group. I have carbons on it. And this is a carboxylic acid. How do you name it? What's the longest chain? With the carbonyl carbon, 1, 2, 3, 4, 5. That's not too bad, but 1, 2, 3, 4, 5, 6, 7, 8. So the longest chain is 8. That's octane. Drop the E, add OIC, and the word acid, octanoic acid. Am I done? Oh no, it's my favorite, the T-butyl group. And you could have put tert, but I'm going to be a lazy organic chemist. T-butyl group, and it's on carbon 3, so that'll be 3-T-butyl octanoic acid. And that's how you name carboxylic acids. If I look at the clock, oh no, we only have seconds left together. Don't forget, tomorrow I will do the alcohol problem set. We'll also have our lab, and the lab you did yesterday is due tomorrow. Next, on Thursday, I will do the ethers and epoxides problem set, because we're not going to have class on Monday. Otherwise, I would have done it on Monday, but we got to get things squeezed in the summer. And with that, don't forget, the lab is due tomorrow. And on Wednesday, tomorrow, my office hours will be from 5 to 6. Same Zoom login. With that, I get to say, Gang gesund, goodbye. Be healthy. Goodbye, Gang gesund.